Doctor, I think there's a new message in the message box.
Yeah. Chen, why minimum as? Okay. Thank you. Yeah, there is a questions from Chen Jia Yi. Why minimum S of 1 over n is none? Why not 1 over n? Can talk explain later. Could I speak a little bit slowly when I speak? Okay, I will try to speak slowly a little bit. All right. Okay, so let me yeah, I have recording now. Okay, yeah, I think I'm actually try to further explain for these examples. I hope you can get a picture. Okay, let's come back to these examples again. So A, B, C, D, E, F. So this is fun. Y increment 0, supremum is 1, and maximum 1, and minimum is 0. Okay, so what you can do is we can look at this. Okay, so S is the set of 1 over n. Take notes for it. S is the set of 1 over n. So there's not only one element, so we have an infinite many of elements. So you can substitute n equals to 1, 2, 3, and so on. So we have 1 half, 1 over 3, 1 over 4, and so on. So that means S has actually infinite many of elements here. Okay, you can look at this, the graph. So when n is 1, the value is 1, right? So that's why we get a value here. When n is 1, so when n is 1, so the value is 1. So we get a plot here. When n is 2, so the value is half. Yeah. When n is 3, we got 1 over 3, so which is somewhere here. When n is 4, I have 1 over 4. When n is 5, we actually have 1 over 5, and so on. So you can see the graph will be like this. Okay. So this is the value 0, right? So you look at a two bound here. You draw a two boundary for it. So I think none of the blue dot beyond this line, okay, is clear, right? So which touch this line. So this is the line 1. This is the line 0. Okay. So since the dot touch the line y equals to 1 here. Okay. So and this is the highest. Okay, this is the highest. Okay. So that's why this is a supremum, and which touch the border here, and maximum 1, 1. Why we get 1 here. Next, you go down here. All the blue dots are always between the line 1 and the line y equals 0. Okay, so this one touch here, so that's why it's 1, 1. But you can see the blue dot never touch this line 0, because 1 over n can never be 0. 1 over n can never be 0 for any n. Okay, we can only say 1 over n approaches to 0 when n to infinity. Okay, but 1 over n can never be 0. So that's why it never touch here. So you can see, and also it cannot go further. It cannot go beyond this line. So that's why the infimum is 0. Since it's never touched the line, so the minimum does not exist. Okay, that's the way. And the blue dot, you can see, since the blue dot touch here, so it is a maximum. Okay, otherwise, which is just a minimum. Sorry, a supremum. Okay, that's the way. So that's why in these examples, so we can see the infimum is 0, no minimum, supremum is 1, and maximum is 1. Okay, in fact, this is actually related to limit. You can see limit for 1 over n is equal to 0. So this 0, then you can see in this example, infimum of S will be 0. Okay, this is the case for it. Okay, next, we do the similar analysis for these examples. The next one, S is this 1 over n. Sorry, n over n plus 1. So you substitute the value inside. So n is 1, we have, you can check it out. So which is half, right? When n is 2, I'm going to have 2 over 3. Then, sorry, the next one will be, when substitute n is 3, 3 over 4, 4 over 5, 5 over 6, and so on. So if you look at this number, 5 over 6, 7 over, so you can see eventually, so this will go to 1. Okay. As you can see, this is the case for it. Okay. This is 1. So like I said, limit for n over n plus 1 is equals to 1. You take note for this. Okay, let's plot the graph for it. So we do the same 1, 2, 3, 4, 5. So this is our n. Okay. So when n is 1, we got half. So which is somewhere. Okay, not a good one. Okay, so maybe put a little bit. Okay, doesn't matter. So then we actually get somewhere here. Okay, half. So when n is 2, we have 2/3. So that is somewhere go up a little bit here. When n is 3, 3 over 4. So here, and then we got this. We got close, but never touch this line. Okay, it's getting closer and closer, but never touch. So similarly, you can see we can draw a lower bound for it. So this is the line y equals to half. So this put here. So this is a line y equals to half. This is a line equals to 1. So and 0 touch this borderline, and none of them touch this upper borderline. Okay, and it never go beyond here. So in this case, then we can see this is the lowest, half will be the lowest, and 1 will be the supremum. Okay, and this dot touch here, so that's why half is minimum, and the blue dot never touch this, so no maximum. That's the case. And again, maybe I don't want to put it over here. This is actually closely related to limit. Okay, as you can see, limit for n over n plus 1 where n approaches to infinity is equals to 1. So you can compare to this number. Okay. Okay, so this is the same picture. We can verify the picture. So you can look at it one by one. When n is 1, we have a 1 minus 1, so we got 0. Okay, so the next one will be 2 plus 1 over 2. Okay, so then it turns out to be 2.5, right? So the next one will be 3 minus 1 over 3. What's the value? So it's about 2.77, something like that. So the next value will be 4 plus 1 over 4. So it turns out to be 4.25, and so on. So you can see this number. So you have 4.25, right? So 224, and then the next one, then is clear, is 4 point something 6. So you can see this one, when you goes on, the value will go to infinity. Okay, and so we do the same. 1, 2, 3, 4, 5. Okay, when n is 1, we got 0. When n is 2, we have something like somewhere here, 2.5 and 2.77, and then 4.25, and so. So you can see all these dots were getting higher and higher, so it no border. Okay, and the border here will be 0. So okay, it will go further up. Okay, there's a no border here. So that's why in this case, then we can get the answer. Increment of S will be 0. This is the lowest. And since this is keep on going up, so no supremum will be infinity, and no maximum. And since the 0 touch the line here, so 0 is minimum. Okay, so this one I'm not going to demonstrate, so you guys go and verify on yourself. So which is actually, you can use the technique same as the example here, okay? So which is actually same as this example. You can refer to this example. You can see after taking the intersection, so this is the set with only one element, okay? Put it properly. Okay, only one element. So since this is only one element, so it must be the increment, it must be supremum, and one is inside, it must be minimum and maximum as well. Okay, so this is how we can get these things. Okay? So this is some of the examples how to calculate the or determine the supremum and infimum. Okay? So the technique will be like this. First of all, you identify. First thing first, you identify infimum and supremum first. Okay, just you can something like that. Infimum will be something that is lowest in the graph. Supremum will be highest in the graph. Okay, and after that, you just need to look at whether which is an element inside the set S or not. If this is inside, so which is also minimum. And if it is not inside, so then it is not minimum. So same, likewise, we can do the thing for supremum and maximum. Okay, so that's the topic for this infimum, supremum, maximum, and minimum. Okay, next we move to the main object, one of the main object here. Okay, so sequence of real numbers. So again, we have discussed just now. A sequence of real number is a collection of infinite many of numbers. So x1, x2, x3. Okay? So I think like what you have learned in calculus. So we just use this notation xk, k from 1 to infinity to denote a sequence. And also we have an idea of subsequence. Okay, idea of subsequence. So if we extract part of the sequence, then will be a subsequence. So we can look at the examples here. So we can consider xk as 1 over k. So the actual sequence will be 1, 1 over 2, 1 over 3, 1 over 4, okay, like our example just now. So we can look at the subsequence of even integer x2k, okay? So that will be 1 over 2, 1 over 4, 1 over 6. Or we can also look at another subsequent x of 2k plus 3. So that will be 1 over 5, 1 over 7, 1 over 9. Okay, we can construct a different kind of the subsequence. So we also have examples here. So sequence xk is -1 power of k. I think it's quite straightforward, right? These things. Xk is -1k, right? So when we look at k, how should I put it? Okay, k, when k is 1, 2, okay, 3, 4, 5, right? So you can see when k is 1 will be -1 power of 1. So this -1 power of 2, -1 power of 3, -1 power of 4, -1 power of 5. So this is -1, this is +1, -1, +1, -1. So that's why this is a sequence -1, 1, -1, 1. So we can also have Okay, so we can also have a consider subsequence for this. Yeah, so let's say the even terms and the odd terms, or some other thing. So again, you should have already learned this limit or sequence in calculus. So I'm not going to go to it, but just recall the limit for it. Okay? So for example, 1 over k, so the limit is 0. Okay, I believe you know how to do it. And this one, the limit also 0. Okay, so for this one, the limit is 3. Yeah? So this thing, you can please refer back to your calculus to how to calculate the limit for it. So you might need to use something so-called the Rupita rule to do it. Okay. So for example, you might need to use, remember. Okay, so to calculate this. So again, we can have this. The limit for k will be infinity, and this is negative infinity. And also, this one, the limit does not exist, yeah, because of like what we have discussed here. So for the sequence, xk is minus 1 power of k, so which is actually minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, and so on. So you can see it will never go to a one particular value. So plotting graph is much more easy to see the picture. So that will be 1. So when we have a minus 1, positive 1, minus 1, positive 1, minus 1. So it keep on up and down oscillating. So it will never focus to one particular value. So that's why the limit does not exist. Okay. So all these you should have already learned in calculus. Okay, next things, then we have the. So we must have a method. Okay, maybe put it this way. From this example, we can see limit of a sequence might not exist. Okay, so that's the thing about it. So that's why we need to look at the other concept for it. Okay, so then we have a new concept. So called the limit supremum and limit infimum. So just to let you know, so these two we always exit. So these two always exit. So how to define this? So then we can see this idea. Okay, to define this limit supremum and limit infimum, so what we can do is we consider this one first, subsequent limit. Okay, so subsequent limit is the limit of a subsequential limit of a sequence is the limit for a subsequence for it. Okay, so that is you identify all the possible limit for it. So S is all the possible limit, and next you look at this all limit, you find the supremum and infimum. Infimum will limit supremum for the sequence. The infimum of the limit will be the limit infimum of xk. Okay, so I think by going through example will be much more easier for you to understand the concept. So we look at this one by one. So for these examples, so for the first one, xk is k squared. So you can see only one limit, right? So you can see only one limit. So that is infinity. So that means in this case, your S will be only one infinity. So since you have only one, so that means you can see a limit infimum of xk. So will be the infimum of S. So since there's only one element, so it must be infinity. So the limit supremum of xk is a supremum of S, so that must be infinity. Okay, so that's the way. Okay, we look at another one. So we look at xk is -1. Okay, so you just list out all the possibilities. So the first one, -1, +2, -3, +4, -5, +6, and so on. So if you look at this, you can see, if you just look at here, then you can see this xk. It will go to +infinity for even number k. You can see all the even number terms, okay? 2, 4, 6, okay, 8, and so on. And also, it will tend to -infinity for odd number k, okay? By looking at -1, -1. So that means there are two possibilities here. So your S will be +infinity, being better fold. And infinity. Okay, so there's only two options here. So then you have no choice, the small one. Then this one must be the increment. So this one will be the supremum. So here you can see increment will be the limit increment, infinity. Negative infinity, limit supremum will be this. Okay, so that's the way. So same as this. Okay, for xk is -1, okay, so s must be -1 and 1. You can check this easily. So therefore, so again, there's no choice. So -1 must be the limit increment. +1 will be the supremum. So same as these examples. I think we look at number 4. Okay. Again, you look at xk is -1k plus 1 over k. So you look at the same idea. So this one will go to -1 plus 0 for odd number k, right? So that's why it's -1. And also it will go to 1 plus 0 for even number k. Okay, so this term always 0, regardless even number or odd number. So this will be +1 or -1. Depends on whether it's odd number or even number. So that's why you can see two possible limit, -1 and +1. So we can have limit increment and limit supremum. Okay, up to this 4 examples are quite straightforward. Okay, so maybe this is a more interesting one. Number 5. So we have 3 different expressions, okay, with all the different value here. So the first one, -k². So this one always tends to -infinity for any value, right? For either. Oh no, this is all odd, because this is all odd, right? So no problem. So we can always this. And next we look at maybe we look at this one, is easier. So 1 over k² plus 1. So this one is clear. When you go to infinity, so this will be 0. Okay. When k go to infinity and k go to infinity. Okay, we look at the one in the middle. 5 minus 1k plus 1. So which is similar to this. And -1 power of k depends on whether it is, the value depends on whether k is even or odd. So this one would tend to -5, okay, for odd value k to infinity, okay, and also this will tend to +5 for even number k when it approaches infinity. So we can see we have a 1 possible, 2, 3, 4. 4 possible limits. So that's why in this case, S will be minus infinity, minus 5, 0, and 5. Then in this 4 number, we just need to identify which one is the increment. So this is the increment. This is supremum. So that's why negative infinity and 5 will be limit increment and limit supremum. And finally, I think this one is clear. Xk is k minus 1 over k plus 1. There's only one possible limit. So limit increment, limit supremum will be xk. Okay, I hope by going through these 6 examples, you guys have some idea how to determine limit infimum and limit supremum for a given sequence. I think example 5 will be a good one. Okay, so you just find out, identify all the possible limits for all the subsequence. Okay, so some behavior or properties for this limit infimum and limit supremum. Okay, maybe this is a more interesting, important one. Limit infimum xk always less of the limit supremum xk. So I think this is clear. The reason is here. So I think this is quite clear. Limit infimum xk always less or equal to limit supremum of xk. Why we can have this? The reason is this is actually equals to infimum of s. This is actually equals to supremum of s. So we know supremum always larger or equals to infimum of s. So that's why we can have this easily. Okay, next will be one of the method to check whether a limit exists or not. When limit infimum equals to limit supremum, so we say limit is equals to a. The limit exists. So that's the way. So if we go back to these examples, I think we can make it bigger. Then we can check this. Okay. So infinity, infinity. So in this case, we can say, so this one, limit is equals to infinity. Okay, for xk. So the second one, this is minus infinity, infinity. So this one, limit not exists. Okay, no limit. So similarly, this one also, limit does not exist. Limit does not exist. Minus 1, positive not the same. Limit does not exist. Okay. Okay, so minus infinity, 5. So this one, limit does not exist. Okay, so limit infimum equals to limit supremum. So this one, then in this case, we can know limit is equals to 1 for example 6. Okay, so we have a very simple criterion to check whether limit exists or not. That is, we can use this method to verify it. Okay. So this is one of the simple criterion to check. Okay. So we can see this. Limit of xk equals to a, provided limit supremum xk equals to a, which is also equals to limit infimum of xk. And we say limit of xk does not exist if and only if limit supremum of xk is not equals to limit infimum of xk. So this is a very important criterion. So we have a simple method to verify whether limit exists or not. Okay. Okay, up to this point, so we are talking about the limit for a sequence of a number. Okay, now we proceed to this sequence of set. Okay. So to define the infimum, supremum for sequence of set, so we use these properties. Okay, so the first one, increment for set. Okay, so which is a little bit different from number. So the increment for AK, K will be, we take the intersection for it. So if you look at here, so we have a running index n here. So we have a different value here. Yeah. Then the supremum, then will be, we are taking supremum of, we're taking the union of it. Okay, so we have a different set of it. Then to calculate the limit infimum, so we're taking the intersection or union for it, and limit supremum will be this. Okay, I think maybe this is a bit confusing, so we are focused more on this. How to compute the limit infimum and limit supremum. So we're using this way. Okay, to compute this C. So what we can do is we can define this. We let B1 to be A1 union A2 union A3 union A4 and so on. Okay, and then we take B2 to be, okay, B1 we begin with A1. Okay, we begin with A1. So for B2, so we begin with A2 and so on. So similarly, we have B3, so that is A4 and so on. So we begin with A3. So from here, we have constructed a new sequence of set B1, B2, B3, and so on. Okay. So from here, you can get these simple properties. That is, you can see here, B1 actually bigger than B2, right? Because we have an extra A1 here, and B3 must be subset to B2 because of we have an extra B2 and so on. Okay, so this is a behavior for this B. So once we have constructed a new sequence of set B n, then we can see, we can define this. So the limit supremum of AK, so that will be we just taking the intersections of all these B. So this is how we can define this, to construct this limit, to compute this limit supremum of AK. So, and if you look at here, each B is a clear union, right? So what you can see is, so this is actually equals to intersections and union of AK. Okay, so that's why this supremum, you can put it this way, supremum union, okay, limit, then we consider intersections. Put it this way. So how to do this? So that is, if you want to put it in a more proper way, so that is, we are putting K running from n to infinity. Okay, you can see, it's sort of like, so 1, 2, 3, right? then you have this. After that, we are taking n from 1 to infinity. So if you just look at here, then just to let you know this, you can see this property. Our Bn is actually, we're taking union k from n to infinity for our AK. So this is how we compute this limit supremum. So that is the formula here. So to compute limit infimum, so we do it similar to this. So what we can do is, we do in this way. We construct C1 to be A1 intersect A2 intersect A3, A4, A5, and so on. And then we're taking C2 and so on. Okay, so this is our C. So and so on. So similar to this one, so you can see Cn is actually, Bn is the union of this. So Cn intersections of AK, K running from n to infinity. So I think maybe I change the color so that you can see the pattern here. So it depends on the running script here. Okay, this is 1, you begin with 1. 2, you begin with 2. Okay, so this is this C. Okay, once we have computed this C, then we can calculate limit infimum of AK. So that is, we just taking union of all the Cn. So n running from 1 to infinity. Okay, so if you follow this actual definition, so it might be a little bit complicated. Okay, however, what you can do is you can follow this procedure to do it step by step. Okay, to compute limit supremum AK, first I think we come back to here. Okay. To do the first step, limit supremum, you begin with B1, B2, B3, and so on, okay, using this way. So once you have computed all the Bn, B1, B2, B3, and so on, then you take the intersection for all the B, then will be the limit supremum of AK. Okay. For the next one will be similar. So to compute the limit infimum, instead of union, we taking the intersection first. C1 will be A1 intersect A2 and so on. And then C2 will be begin with A2, okay, and so on. So, and after that, we taking the union of all the Cn to get the limit increment.
Doctor, hello, sorry.
Yeah.
Can you clarify the roles that K, the indexes play here? K, I understand it's supposed to play the role for the sequence, right? And then what is N here?
N is also a sequence. N to okay, maybe it's a little bit. What you can do is actually you can forget about N. You can write it in a proper way. Confusing for you, maybe frame of AK to be C1 union C2 union C3 and so on. Okay, so the N is actually the running index for this 1, 2, 3. So we just use a shorthand, because if you're writing here, that will be a very long expressions. We use a shorthand as to simplify it here. So that's the meaning of N here. That means N is 1, N running from 1, 2, 3, 4. N running 1, N is 2, N is 3, and so on. Okay, that's the meaning for N here. To running index, we're taking a unit of the C. So similarly, this is the one. As you can see here, maybe again, I change the color so that you can see clearly. Okay. That means you begin with 1. Okay, that's why K running from 1. So K is 1, 2, 3, and so on. 2, then, sorry, this is N, and the red color is N. So the red color is 3, so we begin with 3. So that's why with the K begin with 1, 2, 3. So okay, so K begin with 1, and so on. For C2, K begin with 2, and so on. This is the way to do it. Okay, I think maybe we look at an example, so you can see the idea. Okay, maybe we look at this example. That's the most important part. So just to make sure you can compute these things. So maybe we look at this example. That would be better. Okay, in this example, we look at AK is equals to 0, the closed interval 0 to 1 minus K. So this is the case here. As you can see, so I think this one you know how to compute it. A1 is 0. A2 is 0 to half. A3 is 0 to over 3. A4 is 0 3 over 4. Right? You just calculate, substitute K is 1, 2, 3. You can get this, right? Okay, so maybe you just write down. Okay, so A1 is only 0, and A2 is 0 to half, and A3 is 0 to 2/3, and A4 is 0 to 3/4, and so on. Okay, to calculate the limit, first we compute B. So let's say we compute B. Okay, this. So B1 is A1 intersect A2 intersect A3 and so on. But you can see A1 is subset to A2, A2 is subset to A3, A3 is subset to A4 and so on. So you can see this one eventually, so this will be equals to union of all the AK. Okay, K running from the infinity. So that means you're just taking the union for it. So you're using the method that we calculated. So this is closer and closer to 1, but excluding 1. So you can see B1 is equals to 0 to 1. you can get it. Okay. Okay, we compute B2, so that will be A2 and A3 and A4 and so on. Wait, I think I'm using the wrong symbol here. Sorry, I'm not using N, I'm supposed to using O. So you can see A1 is always subset to A2, right? So that's why with A1 or without A1 wouldn't affect the result. So these two are the same. So you also get this is 0, 2, 1, 2. So we can get this because of you can see easily. So this is just simply because A1 subset to A2. So that's why with A1 or without A1, it won't affect it. Okay, next you can see for B3. So that will be A3 union A4 and so on. So again, you can look at here. A1 subset to A2, A2 subset to A3. So that's why A2 union A3 must be equals to A3. So therefore, this thing must be the same, same as here. So again, because of the same reason here, so because of A2 subset to A3. So you just look at it. B1 is equals to this, B2 equals to this, B3 equals to this. So they are all identical. Right, they are all identical. So that means if you go on, so you can see Bn will be equals to this for all. So if you follow the formula, then we can straight away calculate the limit supremum. So hence, the limit supremum for AK will be, you are taking the union of all the B. Okay, if you want to use a shorthand, this can be written as we taking the union of all the Bn and running from 1 to infinity. So since they are all the same, so this is 0 to 1. Okay, so that's the way to do it. Okay, maybe we look at another way. So we consider same A. So we calculate C1. Okay, in this case, C1 is A1 and A2 and A3 and A4 and A5 and so on. So if you look at here, as I said, A1 subset to A2 subset to A3. So that means all this must be equals to A1 only. So this must be equals to A1. So that means this must be equals to 1 only. Okay. So and C2 will be A2 and A3 and A4 and A5 and so on. And again, all this A2 subset to this, and this is the smallest one. So this must be equals to A2. Okay, so because A2 is the smallest among all these set. C3 again, A3, A4, A5, and so on. So again, A3 will be the smallest among all these. So this must be also A3, and so on. So in general, we can see that in the shorthand, we can see this. We can say that Cn will be equals to An for all, for any integer n. So then we can have this limit increment for AK will be, we are taking the union of all this C. So that will be just A1 or A2 or A3 and so on. Okay, we have actually seen this already in here. So if you are taking the union of all the A, so that will be the closed open interval 0, 1. Okay, so that's why in this case, we also get this, which is also equals to 0 to 1. So in this case, then we can have, in this case, limit increment of AK will be equals to limit supremum of AK. Both are equals to the closed open interval 0, 1. Okay, in this is the case. Right, so that's the way how we compute this limit infimum and limit supremum for it. In fact, because of we have this is a special kind of the sequence, so we don't have to do it in such a complicated way. We come back to this. Okay. So this is a case like this. This is equals to here. So this is a case so-called increasing sequence. So that's why we can compute it in a much more easiest way. Okay. So I think after this, you are more or less know how to compute this limit infimum and limit supremum. Okay. So we go back to this case first. Example this. Okay. So by going through this example, you roughly know how to compute this limit infimum, limit supremum. Okay, let's go to this. Okay, we said that the sequence of set has a limit. Limit AK is equals to A, provided limit infimum equals to limit supremum equals to A. Okay, so these two are identical. Then we say the limit exists, which is equals to the common set. So in this case, we can see limit infimum AK equals to limit supremum AK, which equals this. So we can say, hence, in this case, we can say that limit of AK is equals to 0, 1. Okay, according to these definitions. So, in fact, this example is actually belongs to which one? This is the example for this A. Okay, so this is a special case of the set of sequence. So we said that AK is an increasing sequence. Okay, if we have this. So that is A1 subset to A2 subset to A3 and so on. Okay, so in this example, then we can see actually this is a increasing sequence. Okay, so when we have an increasing sequence, so we can do it easily. So the limit for AK always exists, so which is just the union of all the AK. So we don't have to compute BK and CK. Similarly, a sequence is decreasing when A1 contain A2, A2 contain A3, and so okay, that is fulfill this. Okay, this is an increasing sequence. So when we have an increasing sequence, we taking the union of all the AK will be the limits. The limit always exists. So when we have a decreasing sequence, we just take the intersections. That's always the limit for it. So this is an examples we have discussed just now. This is clearly because of this is an increasing sequence. So that's why we can compute the limit directly without calculate limit infimum, limit supremum, like what I have demonstrated to you. Okay, we can just take the union of all the AK. That will be the limit. So similarly, then we can come to the next example. We can calculate the limits without looking at the limit infimum and limit supremum easily. So we look at this. AK is the closed interval 0 to 1 plus k. So you can see in this case, A1 is what? 0, 1 plus 1, 2. Okay. And what is A2? Remains 0. 1 plus half, so that is 1.5. A3 is 0 to 1 plus 1 over 3, 1.33, and so on. So A4 is 0 to 1.25. So if you look at it, I think it's clear. So you can see this A1 from here we can have this A1 subset to A2. No, I think the other way around. A1 is a superset of A2. A2 is a superset of A3, and A3 is a superset of A4, and so on. Okay, so which means AN is a decreasing sequence. So when this is a decreasing sequence, then we can directly compute limits for AK will be, we're just taking the intersection of all the AK. So if you are taking the intersections, that will be, in this case, will be 0 to 1. Okay, this is a special case to compute. So this is for decreasing or increasing sequence. So for these two special cases, we can compute the limit directly by using these two properties here. Okay, we look at this one. Okay, so this is a general case, so which is neither decreasing nor increasing. So we have to use the definitions to compute the limit infimum and limit supremum for it. So okay, maybe I will do it once again to demo using the method, the general method once again to demonstrate to you guys how to compute limit infimum and limit supremum. Okay, maybe we look at, okay, one first, A. So we look at AK is minus 1 over K. K. Okay, so you can see A1 is equals to minus 1 to 1. And A2 is minus 1 over 2. Minus 0.5 or maybe 1. Sorry, 2. And A3 will be minus 1 over 3, 0.333, and so on, and 3. And A4 is minus 0.25 to 4, and so on. I think maybe this is not a good idea. So I think I write it in a proper way so that you have a better idea how the set looks like. Okay. Okay, as we have done, so this is minus 1 to 1. So A2 is minus half to 2. Okay, A3 is minus 1 over 3 to 3. So A4 is minus 1 over 4 to 4. So if you look at here, so this is actually from minus 1 up to 1 increase. Okay, so this is minus. Okay, next will be, let's say our 0 is here, okay, minus half, so that will be somewhere here. So this is 1, and then it will go to 2. -1/3, so that will be somewhere here, and then we go further a little bit. Okay, -1/4 can never reach 0, and then go to 1. Okay. Okay, maybe I'll put our 0 here. So this is here. So you look at, this is our A. So you can see the right-hand side, this right-hand side, okay, this right-hand side. 1, 2, 3, 4. So you can see when our k to infinity, so this bit will go to infinity, right? So that means the right-hand side will go further and further, so it will go to infinity. How about the left-hand side? -1, -half, -1/3, -1. So this is actually -1. Okay, you look at the limit when k to infinity, so this would reach 0. Okay, so this part will go to 0. Okay, at least you have some idea for it. Okay. Okay, now we can start one by one. So B1 is A1 union A2 union A3 union A4. Okay, you combining all this line. So we remain here, this part, and then we join this. Okay, we joining. So that means this is actually, you look at you combining all this line. So this will be -1, 2. Okay, maybe it should be. So this is -1, 2, infinity. Okay. Okay, B2, we begin with A2 union A3 union A4 and so on.
Dr. Lu, just to ask, when it comes to infinity, does it matter if it's open or closed?
In here, when you take the union, it's always open. We always exclude the infinity.
So when we are bringing infinity, the interval must always be open, lah. Is that what you're saying? Or only in this case?
No, I don't. Okay, you have to look at where is this. Okay, so how should I say this? Okay, maybe I open up another 1, 2. No, it depends on how you're going to evaluate the case. So for example, if you look at this, you look at limit of n to infinity. Okay. So this one, you can see it will be, you look at the line here. Okay. So when 1, the value is 1. When 2, 2. When 3, 3. So you can see this bit will blow up to infinity.
Okay.
So and infinity is not a number, so that's why you cannot always we are not going to include this thing. So that's why when you look at it, 0 to n, whether you include or not include. So this will be okay. This part will not change, right? So 0 to infinity. Okay, because this is a number. Infinity is not a number. It can never include the infinity. Okay, at least here at this stage, this is the case here. Okay, but however, if you
so would there be situation that it can include infinity, or no?
That will be yes, but let me see. Are we going to discuss that situation? I also can't remember. Yes, we can have things like that. For example, negative infinity up to positive infinity. But this is something that is a more advanced kind of the concept. Okay, this is something more advanced. I also can't remember whether are we going to discuss this in chapter 4 or 5. I also can't remember. Okay, let's suppose up to here at this stage. Okay, we are living in our real world. Okay, we are living in our universe. We wouldn't cross the border of the universe. Okay, we can never reach that. At least in this chapter 0. In chapter 4 or 5, I'm not sure whether we're going to do that or not. I can't remember.
Okay, understood.
Okay, all right. Okay, yeah. Right. So that's why it depends on how it, but of course, if you're talking about these things, something like I also lost already, maybe in the -1/n, something like that. Okay, and then this thing that you will not go to infinity, right? So that's the picture. But that's another story. Okay. Okay, forget it. Okay. Okay, yeah, we come back to here. So for B2, so again, if you exclude this, okay, exclude A1. So let's say we just exclude. Okay, so okay, we begin with A2, exclude this one. A2 join with A3, joining with A4, and so on. So we can see this will be remain here, and then we keep on adding this, extend this to infinity. So you can see B2 it end up to be -12 to infinity, right? And similarly, when you come to B3, we begin with A3 union A4 and so on. So we begin with A3, so that means we begin from here. So similarly, we can get this is -1/3 up to infinity. Okay, so in general, so you can see B4, I think you can guess the pattern will be, I think I give you B4, I think you may able to guess the pattern, so that will be -1/4 to infinity, right? So if you go to in general, that will be Bn will be -1/n infinity. Okay, this is the general pattern for Pn. So then we can calculate the limit Supremum, sorry, of AK will be equals to, we are taking, the intersection for all the Bn. So we can see, okay, this is 0 to infinity. So this is how we compute this limit Supremum of AK. So this is this stage here. So to compute the limit Supremum, then we do it this way. Okay, we compute 2 3 and so on. Okay, so to do this, maybe we can come back to look at the okay, we look at here. So C1, we are taking the intersection of all these things. Okay, so we are taking the intersection of all this set. Okay, so you look at here. If you are taking an intersection, so if you intersect this bit gone, so you're up to here and up to here. If you're taking an intersection, so that will be 0 up to 1. That will be our C1. Okay. So you can see, just look at our A. So you can see this is actually equals to the set 0 to 1. And similarly, so we calculate C2 again. We begin with A2. So you can check the set A. You can see this is actually 0 to 2. And you calculate C3. So you begin with A3, A4. So we can see this is 0 to 3. So if you follow the pattern here, C1 up to 1, C2 up to 2, C3 up to 3. So you carry on. So Cn will be given by 0 to n. Okay, once you have obtained the Okay, can you hear me?
Yes.
Yes,
Yes.
Okay. I think something wrong with my plug. I'm actually plugged in my computer, so it suddenly my battery flat. Okay, never mind. So let's carry on with this. Okay, once we are able to get the expression for our C, then we can directly use it to compute our limit infimum. So in this case, so the limit infimum for AK, so that will be the union of all the Cn. N running from 1. If you are not comfortable with this symbol, so that is actually just you're just combining all the C, okay? C1, C2, C3, and so on. Okay, so because of I think take away the ruler, so you can see this is a minus. This is 1, 0, 1, 2, and so on, right? So that means if you're adding, so this will become 0 to infinity. So in this case, yeah, you can see this is the answer. So limit supremum is the closed interval 0 to infinity. Limit infimum is closed interval 0 to infinity. So they are the same. Okay. So in this case, so the limit exists. So limit of AK will be this. So that's the way. What you need to do is you just do it step by step. Okay, you look at the pattern for your AK. Maybe if you want, you can list out the first few terms for A. You list out A1, A2, A3 like this. Okay. What you can do is you're doing things like this. You list out the first few terms for your A1, A2, A3, A4. Okay. And then you're using this to compute your B and C. What is your B? B is taking the unit of them. So B1, B2, B3, you compute it. Okay. Once you have identified all the B, then you are taking the intersection of them. And then you will get a limit supremum. Likewise, to compute the limit infimum, you just compute the C. C1, C2, C3 using this way. Okay. Again, after you have computed the first few terms for your C, then you more or less can guess the pattern for the interval C. Okay, and then you are just taking the union of all the C, then you can get your limit infimum. So that's the procedure. Okay, I don't think this is a very difficult process. It's just that it might be very troublesome. So you just need to write down all the set one by one. It takes time for the beginning at the beginning stage. Okay. However, if you already familiar with all this intersection union of set things, then this shouldn't be any problem for you, right? Okay, so let's proceed to this one. So this one, I don't think I need to give you demonstration, so you can verify yourself. So AK is the close open close interval 0, 1 when K is odd, and which is open close interval 1, 2 when K is even. So that means this is the way. Okay, where is the B? Oh, do I need to write now? Okay, maybe. So maybe we carry on with this. So this is quite straightforward. A1 is 0, 1, and A3 is the same. A4 is the same, and sorry, A is 5, not 4. A5, and so on. And next for the even terms, that will be 1, 2, 2. A4 is 1 to 2. A6 is 1 to 2, and so on. Okay, so this one, you just use a similar method to do it. You can see B1 equals to B2 and so on, all equals to 0 to 2. Okay, you can verify on yourself. What you can do, you take the union of all this, you get B1, and so on. And then you can see C1, all the C are empty set. Okay, just demonstrate this one. For example, you can see example, just example. So let's say C3 will be A3 intersect A2 intersect, A4 and intersect A5 and so on. And because of the even terms are all the same and all the odd terms are the same, right? So actually you just need to do the intersection for two of them. So 0 to 1 intersect with 1 to 2. So this will be empty. Okay. I think I better use a green color. Okay, so this is an even term, this is the odd term, so we will get empty set. So likewise, you can calculate all the B, so which is you just taking a union of these two things, so that will be 0 to 2. So then you're taking, since all the B are identical as well as all the C are identical, you're taking the unit intersection of B, you get this. Limit infirmary is this. So in this case, these two are not the same. Okay, so limit does not exist for the case. All right. So just to make sure you know how to compute this limit infirmary and limit supremum. First of all, if I give you a sequence of set, yeah, just a revision again, how to compute your limit infirmary, limit supremum. Okay, that's the way. This is the one, these things. I think maybe this will be better, right? Okay, we'll refer to this one. Okay, so to compute limit supremum, what you need to do is you just do it one by one. First, you compute B1 will be this. You're taking the union of all the A, and then B2 you're taking union of all the A, begin with A2, and then B3 you're taking union of all the A, begin with A3, and so on. From here you can get all the B. Right? After that, to compute the limit supremum of AK, you just take the union of all the B. So you just go through two processes. First, compute B, and then you take the intersection of all the B. That will be a limit supremum. Okay. Similarly, to compute the limit infirmum, so we begin with calculate C1. We taking a union of all the A, begin with A1, and then taking the union of all the A, begin with A2, take intersection of all the intersection, begin with A3, and so on. Then you use the formula to calculate limit infirmum. That will be this. Just go to two process, okay, to calculate this. Yeah. So I think it's not difficult. It's just that you might need to take some time to identify each of the B1, B2, B3, C1, C2, C3, and so on. Okay. Well, so I think about 4 minutes to 9:30. Okay, I think I should stop here now. Okay, before that, you get any questions? Any questions?
Sorry, Doctor.
Yeah.
If I were to refer to the book, which chapter would this be from?
Which book you are talking about?
This is from the car book, right?
Sorry, where's my book? I don't have my book with me. I think this is in chapter 3. Let me see. Just 1 minute. Sorry, I don't have my book with me. Let me see. Can I find? Can I have a content? Oh, okay. I'm not sure whether it's available. Oh, it's not. Where is it? Sorry, I can't remember. I don't know where is it. You can check the index. Okay, you see the limit increment, limit supremum. You should be able to get it. Okay. However, I think there is no discussion on the limit increment for numbers. So that means this part. For this one, limit increment for number is not discussed in this Alan Carr book, because in a way this is actually should have discussed in the calculus in the undergraduate level. Okay, you may refer to any books of the real analysis. Yeah.
Oh, okay. I kind of already uploaded. Sorry, the book on the chat actually.
Oh, okay. Where do you get this book? Very nice. This is okay.
Somewhere. Okay.
Okay.
Yeah.
So Santa Claus. Okay, I think better off record.
Yeah.
Okay. Sorry. Hey, where to switch off? Let me see. How to where is it? Hey, just 1 minute.
Doctor, are you there?
It's still recording? It's still recording? Okay, stop record. Okay.